So dual nature of electromagnetic radiation is that electromagnetic radiation behaves like a wave and also like particle. All electromagnetic radiation travel with the speed that is equal to the speed of light, that is given by C is equal to 3 into 10 power 8 meter per second. Unlike continuous spectrum, atoms in gaseous phase emit or absorb only specific wavelengths. It is not in a continuous range. Hello dear students, I am Roja, your chemistry lecturer from Vidhyaashram PU College, the Temple of Excellence, Mysuru. So we shall continue the chapter Structure of Atom in today's session. Previous session we have learnt about discoveries of subatomic particles, then also about atomic models. In this session we shall learn about developments that is leading to Bohr's atomic model. What are the factors that led to the development of Bohr's atomic model? We shall study now. Niels Bohr modified Rutherford's atomic model based on the spectroscopic studies. So in that he observed that dual nature of electromagnetic radiation and also about experimental results that is based on atomic spectra. So dual nature of electromagnetic radiation is that electromagnetic radiation behaves like a wave and also like particle. So when they behave like wave, they explained diffraction and the interference phenomena. When it behaved like a particle, it explained photoelectric effect and the black body radiation. And this concept was crucial for understanding energy quantization. So that we will study later. Now experimental results on atomic spectra gave when atoms absorb or emit energy, they produce line spectra, that is series of discrete wavelengths. And then these observations suggested that electrons occupy specific energy levels and not random orbits. So Rutherford atomic model suggested that electrons would revolve around the nucleus but not in a specific orbit. So that is wherein this experimental study on the atomic spectra gave that these electrons will rotate in a specific energy level, or it can be called as discrete orbits. So now we shall study about wave nature of electromagnetic radiation. So when electromagnetic radiation behave like wave, what are the characteristics of those radiations? So electromagnetic radiations refers to waves that consist of electric field and magnetic fields that is oscillating at right angles to each other and to the direction of wave propagation. So if this is the direction of wave propagation, this line represents electric field, and to the electric field the magnetic field is perpendicular to it. Then these waves do not require a medium to travel, that can move in vacuum also. All electromagnetic radiation travel with the speed that is equal to the speed of light, that is given by C is equal to 3 into 10 power 8 meter per second. The energy of an electromagnetic radiation is directly proportional to its frequency or inversely proportional to its wavelength. So therefore, energy is directly proportional to nu. Nu represents frequency, or it is inversely proportional to wavelength. So lambda represents wavelength. Now these electromagnetic radiation leads to a spectrum. A spectrum is nothing but an arrangement of different types of electromagnetic radiations, either in the order of increasing wavelength or in the order of decreasing frequency. So it leads to gamma rays, X-rays, violet rays, infrared, microwave and radio waves. It is based on the increasing order of the wavelength or the decreasing order of the frequencies. So that is band of colors that is arranged according to the increasing order of the wavelength. So now let us see what are the different regions of the spectrum. So there are mainly concentrated on radio waves, microwaves, infrared, visible and UV rays. Radio waves lies at around approximately 10 power 6 hertz. Hertz represents its frequency, so it is based on the frequency range. This sort of waves are used in broadcasting. Microwaves lies in around approximately 10 power 10 hertz. So it is used in radar. Infrared region is around approximately 10 power 13 hertz, which is used for heating purpose. Visible light is around 10 power 15 hertz, that is what we are able to see. Ultraviolet region lies around 10 power 16 hertz. So that is emitted by sunlight. The two properties that characterize the electromagnetic radiations are, one is wavelength and another one is frequency. So what is that wavelength and the frequency are? Wavelength is the distance between two adjacent troughs, or it can be between two adjacent crests, and the unit to measure the wavelength is meter. So, the highest point or a peak that wherein the maximum displacement has taken from the equilibrium position is called trough. The distance between the adjacent trough gives the wavelength, or if it is crest, like the lowest maximum peak that has given the negative displacement from the equilibrium position gives crest. So, the distance between the adjacent crests gives the wavelength. Frequency is the number of waves that pass a given point in 1 second. So, that is the frequency which is expressed in hertz or per second. The relationship between the velocity of light, wavelength and frequency is given by the equation C is equal to h nu, or it can be rearranged as nu is equal to lambda by c. The wave number is defined as the number of wavelengths per unit length gives the wave number, and it is expressed in per meter. Therefore, wave number is given by nu bar is equal to 1 by lambda, and the unit is per meter. So, that was about wave nature of the electromagnetic radiation. Now, the particle nature of electromagnetic radiation was given by Max Planck. So, it is named after him, that is called as Planck's quantum theory. So, wave theory was able to explain only diffraction and interference of light, but failed to explain black body radiation, photoelectric effect and variation of heat capacity of solids with temperature, and then line spectrum of hydrogen. So, then Max proposes some theories. He gives some postulates regarding the particle nature of electromagnetic radiation. That is, atoms and molecules could emit or absorb energy only in small discrete quantity called quanta or photon. So, he says energy is not continuous, it comes in a discrete package, that is called photon. The energy of quanta of radiation is proportional to its frequency and is expressed as E, that is directly proportional to frequency. This proportionality constant is removed and then added equals to an proportionality constant, that is h. H is equal to Planck's constant. It has numerical value 6.626 into 10 power minus 34 joule second. Then energy is always emitted in the integral multiples of h nu. Therefore, it is given by E is equal to n h nu. N represents multiples of numbers, that is, it can be 1, 2, 3. Max Planck could be able to explain the other phenomena called as photoelectric effect. So, what is this process? So, in this process, it consists of a tube wherein we consider a metal surface and a detector on the opposite side. So, when the light hits on the metal surface, it would eject electrons, and these two ends are connected to high voltage source. And then in this process, the emission of electrons would take place only when a light of suitable frequency would hit on the metal surface. So, such phenomenon is called as photoelectric effect, and it depends on the intensity of the light that is going to hit on the metal surface. The ejected electrons are called as photoelectrons, and the elements that are able to exhibit photoelectric effect are like alkali metals, which include cesium, rubidium, potassium and sodium. So, let us now see what are the experimental observations that were observed by Max Planck. That is, first thing is there was no time lag, that is, the electrons are ejected instantly when the light of suitable frequency strikes the metal, and therefore, the number of electrons depends on the intensity, that is, more intense the light is more of the electrons that could eject. So, the other factor is threshold frequency. Below a certain frequency, no electrons are ejected no matter how bright the light is. So, such type of frequency is called as threshold frequency, and therefore, the next factor is kinetic energy depends on the frequency, not on the intensity. So, higher the frequency of the light is, more of the kinetic energy of the ejected electrons. For example, red light with lower frequency will never eject electrons because it is below the threshold frequency, but then if very bright weak yellow light is of higher frequency, then they would eject electrons. So, it depends on the threshold frequency also. So let us see now the particle nature of electromagnetic radiation that is given by Einstein. So his explanation is known as photon theory. It was given around 1905. So light behaves as particles were called as photons, and each photon has an energy is equal to h nu. Here again h is known as Planck's constant, which is having a numerical value 6.026 into 10 power minus 34 joule second. Then nu is known as frequency of light. To eject an electron, photon energy should be greater than or equal to work function that is given by W naught is equal to h nu naught. Frequency is greater than nu naught, that is threshold frequency. Electron is ejected with kinetic energy that is given by MeV square, that is mass into velocity, is equal to h nu minus h nu naught, wherein Me is the mass of electron and V is the speed of the electron. So let us now study about atomic spectra as evidence for quantized electronic energy levels. Thus, that means when atoms absorb energy, the electrons get excited to higher energy levels, but then these excited states are unstable, so electrons will not stay there for a longer time. So therefore, electrons return to a lower energy levels by emitting energy in the form of light or radiation. So therefore, the light that we see is because of the emitting of electron when it moves from lower energy level to higher energy level. The energy difference between the levels determine the wavelength of the emitted light. So let us now study about the types of spectra. So let us see about continuous spectrum. So this continuous spectrum is produced when white light passes through a prism. So therefore, it shows a smooth range of colors from violet with having a higher frequency to a red which is having a lower frequency without any gap. Example is a rainbow wherein you can find the continuous form of colors. So there is no gap in between the colors. Therefore, white light contains all the wavelengths of visible light. So this is actually the continuous spectrum. There is one more type of spectrum, that is emission spectrum. So this type of spectrum is produced when a substance that absorbed energy emits light as it returns to a stable state. Therefore, it shows bright lines on a dark background at specific wavelengths. So this type of spectrum indicates that only certain energy transitions are possible and therefore energy levels are quantized. So this is the emission spectrum wherein you can see bright lines on a dark background. That is because it is only absorbed certain energy levels. So one more type of spectrum is absorption spectrum. It is produced when continuous radiation passes through the substance and some wavelengths are absorbed. It is also the same, only certain wavelengths are absorbed. Therefore, it appears as dark lines in a bright continuous spectrum at specific positions. So this is the absorption spectrum where you can see there is a gap in between the lines in the continuous spectrum. So that is darker lines on the brighter background. So missing lines correspond to the absorbed wavelength. So the other type of spectrum is line spectra, which is also known as atomic spectra. Unlike continuous spectrum, atoms in gaseous phase emit or absorb only specific wavelengths. It is not in a continuous range. These appear as bright lines like emission spectrum or darker lines which acts as an absorption spectrum, and hence it is called as line spectra. So here in this process, a gas discharge tube is placed and then a slit is being placed in front of the gas discharge tube containing a gas. Then prism is parallelly placed in front of the slit. Therefore, when the gas passes through the slit, it shines on the prism, giving both emission spectrum and the line spectrum of absorbed specific wavelength. Rydberg generalized this to all hydrogen spectral lines, which is given by wave number is equal to RH bracket 1 divided by N1 square minus 1 divided by N2 square per centimeter, wherein N1 starts from 1, 2, 3, which represents lower energy levels. N2 represents N1 plus 1, comma N2 plus 2 and so on. It represents higher energy levels. So hydrogen spectrum consists of certain series known as Lyman series, Balmer series, Paston series, Brackett series and Pfund series, wherein the Lyman series starts from N1 is equal to 1, which is available in the UV region. Balmer series lies in the visible region, so N1 is equal to 2. Paston series lies in the infrared region. In the same way, bracket series also lies in infrared. Along with that bracket series, P-Fund series also lies in the infrared region. When electrons absorb energy from the lower energy level, that is N equals to 1, it jumps to higher energy level and comes back to the same lower energy level by emitting the electrons in the form of light or photon. Using all these phenomena, Bohr's model of hydrogen atom was proposed, and Bohr's model of atom was only restricted to hydrogen atom, not for the higher elements, and therefore it says that it is of around stationary orbit. That means it is fixed orbits, that is they don't move around. Electrons revolve around the nucleus in a circular orbit of fixed radius, and the energy that is called stationary state. So, no energy is emitted while the electron is in this stationary state. So, it also says about energy absorption and emission, that is electrons jump between orbits when they absorb or emit energy. Energy is not continuous, it is absorbed or emitted in the form of quanta, and therefore energy change is given by delta E is equal to E2 minus E1, which is equal to h nu. And the other factor is angular momentum quantization, that is angular momentum of these electrons is quantized, which is given by MEVR. Me represents mass of the electron, V is velocity, and R is the radius of the atom, is equal to NH by 2 pi, wherein N is equal to 1, 2, 3 and so on. And therefore, what about the energy level is, and each orbit has a definite energy which is given by En is equal to minus 2.18 into 10 power minus 18 divided by N2 joules for only hydrogen atom. So, that energy level is given by this factor. So, let us see what are the limitations of this Bohr's atomic model, that is, so could not account for fine structure, that is doublets, too closely spaced lines in the hydrogen spectrum, which is observed with high resolution spectroscopic techniques. And also it is failed to explain the spectra of atoms other than hydrogen. For example, helium atom, even though helium has only 2 electrons, it was not able to give the proper explanation for that series. Could not explain splitting of spectral lines, that is in the form of Zeeman effect or Stark effect. Zeeman effect in the presence of a magnetic field that would take place. Stark effect that would take place in the presence of an electric field. And the last thing is, it was not able to explain how atoms form molecules by chemical bonds. So, it was only for the hydrogen atom and failed for the higher elements. So, due to these limitations, there was a need for advanced theory that could explain complex atomic structure and details about spectral lines and also about chemical bonding. So, that was given by quantum mechanical model of an atom. So, let us see what is it about. Bohr's model was a big step forward, but it had limitations, especially for explaining the structure and spectra of complex atoms. It was only limited for the hydrogen atom. To overcome these shortcomings, a more general and accurate model was needed. So, the two key developments that led to the quantum model were dual behavior of matter, that is given by de Broglie, known as de Broglie hypothesis. So, it says in 1924, Louis de Broglie proposed that matter has dual nature similar to that of electromagnetic radiation. So, it behaves like wave as well as particle-like. So, particle-like properties, for example, mass and momentum, and wave-like properties like wavelength were explained by de Broglie hypothesis. Just as photons, that is light particles, have momentum and wavelength, electrons also have both. So, that is what is given by de Broglie. So, with this equation called lambda is equal to h by mv is equal to h by p. P is known as momentum, which is given by mass into velocity of the electron. H is, it is Planck's constant, which is given by the numerical value 6.626 into 10 power minus 34 joule second. So, the another development that led to the quantum's model were Heisenberg's uncertainty principle. It states that it is impossible to determine simultaneously the exact position and exact momentum, or it can be expressed in terms of velocity of an electron. So at simultaneously you cannot determine the exact position of an electron or mass of an electron. So if position of an electron is known, then the momentum of electron will be smaller and vice versa. Therefore, the uncertainty principle equation is given by delta x into delta p greater than or equal to h by 2 pi, where delta x is uncertainty in position, delta p gives uncertainty in momentum, that is mass into velocity. So what are the significance of this thesis is, there is no definite path or orbit for electrons to revolve around the nucleus. It is applied to microscopic, not for the macroscopic objects. So microscopic here in the sense it is electrons. Macroscopic can be of anything that is visible to our eyes. So this was about today's session. In the next session, we shall study about quantum mechanical model of an atom. So thank you.